A traditional microscope allows us to view the details of small objects using visible light. But visible light only provides information about the color and shape of an object. However, a microscope using infrared radiation instead of visible light can obtain microchemical information, revealing the true nature of the sample. Infrared radiation for microscopy is generated in one of two ways: a thermal source or a quantum cascade laser, QCL for short. Thermal IR sources are diffuse emitters of infrared radiation that spread their power over a broad spectral range. In contrast, QCLs can generate coherent infrared radiation at discrete, selectable wavelengths. Its high brilliance makes the QCL radiation more focused at a much higher intensity. This can be leveraged to increase signal-to-noise ratios, making QCL perfect for microspectroscopy. This higher spectral power density, however, comes at the cost of a reduced spectral range, which significantly limited the use of early QCLs. Luckily, today's QCLs can cover the full molecular fingerprint spectral region, and the time is right to discover the new applications of QCL microscopy. QCL microscopy is tightly linked to classic IR and FTIR spectroscopy. While FTIR spectroscopy observes all wavelengths in the infrared range simultaneously, QCL spectroscopy can select individual wavelengths to solve defined problems much more efficiently. This is best explained by using a relatable real-life example: microplastics. Microplastics can be found basically everywhere. When looking at water samples, environmental scientists typically want to know about the identity, size, and number of microplastic particles. FTIR is perfectly suited to answer these questions. Although the scan can take several hours, complete filters can be scanned to obtain a very detailed chemical image of the microplastic contamination. However, if you want to screen a large number of samples, you would quickly amass quite a backup. Now, if you already know which type of microplastics you're looking for, QCL spectroscopy can be focused solely on the specific and optimal infrared range, generating a beautiful high-contrast image and present you with a very quick answer to how many. Just how quick is QCL? Well, to put this into numbers, scanning a filter area of about 100 square millimeters, FTIR would take 2.5 hours, while QCL could get the job done in just 25 seconds. A true powerhouse. Remember, though, that QCL only looks at a very small and specific part of the infrared spectrum, and thus, the speed advantage quickly fades as we need to acquire more spectral information. That makes FTIR spectroscopy indispensable. The best option would be a seamless combination of FTIR and QCL technology. As QCL technology rapidly emerges from infancy, we see new applications rising too. In life science, IR microscopy is already being applied for label-free biotissue analysis. However, QCL would not only improve performance, it could also pave the way towards future, more efficient diagnostic techniques. Pharmaceutical development can also benefit enormously, as QCL's high throughput is a key advantage throughout the drug development process, from initial research to end-stage quality control. But more importantly, QCL opens the door to completely new infrared microscopy applications. Currently, QCL is used to study the movement of live microorganisms in water and to monitor yeast fermentation in microbioreactors in real time. Naturally, life sciences are pioneering QCL technology. But a huge potential lies in the real-time investigation of dynamic processes in material sciences to reveal physical and chemical reactions on a microscopic level, at video frame rates. Bruker is always on the lookout for new, exciting, and world-changing technologies. And QCL is certainly one of them.